Hi, I'm Tim.
I'm Ryan.
Hopefully by the end of this presentation you will understand why, when we send something like a satellite into space, we need to put it into orbit so that it doesn't fall back to the Earth.
There are lots of misconceptions about orbits. For instance, that astronauts feel weightless because there's no gravity in space. But if this were the case, then why do we put satellites into orbit in the first place? Well, let's begin with an example. Say we had a very tall tower, 400 kilometers tall for instance, which is about the distance the International Space Station orbits the Earth at. Would there be a force of gravity acting on someone standing at the top of this tower?
Well, we know that the moon is kept in orbit by the force of the Earth's gravity. And the moon is 10 times as far as the International Space Station, so there must be a force of gravity at the top of this tower. In fact, Newton found that the force of Earth's gravity is equal to a very small constant g, multiplied by the mass of the object in question, multiplied by the mass of the Earth, all divided by the distance between the centers of mass squared. Therefore, the force of gravity at this tower is about 89% of the force of the gravity here on Earth's surface. So if we were to drop a soccer ball from this tower, it would fall to the Earth and land at the base of the tower.
Say we were to kick the soccer ball off the tower. We would watch as the ball fell back to Earth, but this time it would land much further from the base of the tower. In theory, we could keep kicking the ball harder and harder and probably would need to get something a lot stronger than our foot, until eventually for every meter the ball was falling back towards the Earth would curve a meter away from the ball. This is an orbit. The ball isn't canceling out gravity, but rather it's moving so fast horizontally to the Earth that it's stuck in a state of perpetual falling.
Now that we know how orbits work, we can figure out how fast we need to kick the ball in order to send it into orbit. In order to figure this out, we can use Newton's second law, which most of you have probably heard of, force equals mass times acceleration. Imagine a car traveling around a circular racetrack with a constant speed. At this point, P1, it will be traveling at that moment with a velocity tangential to the circle. At point P2, it will be traveling with a velocity also tangential to the circle. However, this time it's facing a different direction.
We know that the acceleration is a change in velocity over a change in time. And as we can see from these two velocities, the direction of the car changes as it goes around the circle. In order for the direction of the car to change, there must be an acceleration that changes the direction of the car. We can draw that change and see that it points towards the center of the circle. Therefore, the acceleration of the object in circular motion is always towards the center.
Physicists have proven with a little bit of calculus that the magnitude of the acceleration towards the center of the circle when moving in circular motion is equal to the velocity of the object squared divided by the radius of the circle. We don't quite have the time in this video to explain this equation, but if you're interested, there's plenty of simple explanations on YouTube. Now, let's take this information and use it with Newton's second law.
We can replace F in the equation with the force of gravity since that's the only force acting on the ball while it's flying in orbit. We know that when something is traveling in a circle, its acceleration is equal to v squared over r, and since we want our ball to be flying in an orbit and not falling back down to Earth, we plug in this for our acceleration. Since that ensures the ball flies in a circle and doesn't either 1, crash into the Earth, or 2, get kicked so hard that it flies out of orbit away from the Earth.
Doing some simplification, we arrive at the equation velocity equals the square root of g times the mass of the Earth divided by the distance of the surface plus the radius of the Earth. Because the force of Earth's gravity isn't centered on the surface of the Earth, we need to account for the Earth's radius, not just the height of our orbit. Plugging in these values to the equation, we get that the velocity of the soccer ball is 27,023 kilometers an hour, roughly 270 times faster than you can legally drive on the highway. You're going to need something much more than the power of your foot to kick something that hard. So now we know things in orbit are going ridiculously fast in order to keep away from Earth's surface. That still doesn't explain though why people in orbit feel weightless. If there's still gravity in space, and the gravity is essential to keep in orbit, why don't astronauts walk along the bottom of their spaceships while they're in orbit?
Well, as mentioned earlier, the astronauts in the spaceships are basically always in freefall towards the Earth. They're just missing the ground because they're going so fast. Astronauts standing on a scale in the ISS don't get a reading for the same reason someone doing a skydive from an airplane wouldn't get a reading if they stuck a scale below their feet. The only differences are that 1, there's no air resistance pushing back against you in space since the Earth's atmosphere doesn't reach into space, and 2, after 2 minutes, you aren't going to crash, since you're perpetually falling and not actually getting closer to the ground while in orbit.
Just to recap, there is still gravity in space, and the reason satellites and other things can orbit is because for every bit they fall towards the Earth curves that much away from them.
We can figure out the speed something needs to get into orbit given the distance that it is from the Earth, and know that astronauts still have weight, it's just that everything around them is falling at the same speed they are. Thanks for watching!